Hey guys, and thanks for clicking on this video. So this is part 3 of our drone series, probably the second last part. The next part will fly and crash. But yeah, I'm trying to break it down in small steps. As you can see, I really want you to, if you watch all 4 videos, you'll be able to build yourself and understand why you built it. So if you just want a drone, then just wait till I release the files and Bob's your uncle build a drone. So in the first video, we discussed the PCB, we discussed the KiCad, why we chose the components, what we did. Second video was more about the components we bought, because I'm not going to make a motor myself, the housings, the blades, and just discussing more about that. In this video, I'm going to speak about the programming. So I'm using Arduino IDE, that's just easier for everyone. And the ESP32 can work with Arduino IDE. And then we're going to discuss about how you get information from the accelerometer, how to PWM the signals to your motors, because it's important to know that the Arduino and the ESP32 PWM signals are different. They both are PWM signals, but with Arduino you can do analog write. With ESP32 you can't. You have to use a thing called LEDC write. So I'll talk more about that. So guys, if you want to see more of this video, just relax, thumbs up, subscribe. If you just want to see more of this amazing hair that is going to happen in this lockdown, like, subscribe, because yeah, I can't cut my hair until end of February, so we'll see where this goes. Maybe Dragon Ball Z style this. But anyway, that's not why you're here. If you're here, it's fine for that. Let's get started. So a very important concept in the drone programming is a term called PID, Proportional Integration Differential. So I'll put a link below about people explaining PID much better than I can, but just to speak about it broadly, it's basically just a way to stabilize your drone. So when I have a drone here and it tilts a bit this way, I need my motors on this side to push harder than these to make myself center again. So PID smooths that out for me. So if I do it too fast, it will go too far. So what PID does is will go fast until it gets to a certain stage and then slow down and then stabilize. So PID helps with the oscillation. So if I just say, okay, increase speed until you go past a set point, so it's my set point 0. So if I'm in this position and I want my back in my set point to be 0, these motors need to push up and these motors need to be less thrust. And then I will stabilize like this. But I can't just keep going like this because it will keep oscillating. So PID will increase, slow down a bit, and then stabilize. So I'll speak more about it in this video. That's the basic of it. So PID is very important. So if I go up, my back motors need to push harder. If I go forward, my front motors. And how they speak to one another is with the accelerometer. So the accelerometer checks where I am, I get that information, I process that information, and I send it to my motors. So that's the basic control systems of the drone. I've got an input, which is my accelerometer. I've got feedback, and then I push my motors depending where I am. So it's a feedback loop. Cool, let's look at the code. So let's chat about the accelerometer, the MPU 650. So as I mentioned earlier, I've got the libraries that I used to get the information from the accelerometer. I did not program this myself, so I will put the library below on GitHub where you can download it. But I'll just go through it slowly. So the MPU 650 uses a protocol, a communication protocol called I2C. So you can see it here. You got your SCL and your SDA. So when you look at the schematic that we did, these are these two lines, SDL, SDA, which goes to my ESP32 over here. So I2C always needs some sort of pull-up resistors on the communication line to get it working. So always remember to add the pull-up resistors on your I2C. If you want to learn more about I2C, I'm sure you can just YouTube it, but it's just a communication protocol to get information from different devices on your microcontroller. And then what you also have to take note about is your interrupt pin for your MPU 650. So you can see INT over there, number 6. So this is my interrupt that goes to my ESP32 and interrupt. So this just interrupts my ESP32 when it's ready to give some values, and then my ESP is listening. Okay, I've been interrupted, let me capture where this accelerometer is. Another important thing is the address of your MPU. So you can either, with this resistor, pull your address high or low. So I chose to put it low as the default, and that means your address is 0x68, so just 68 hex. If you pull it up, you will get 0x69. So let's just quickly browse through the code and just speak about some stuff. I'm not going to get into too much detail because I2C and this program by itself is it's a different topic. We are just making use of something that someone already did for us and use it in a program that we need. So you can see they've got some arrays storing your pitch roll, your Euler angles. That's what I spoke about, the interrupt detection. So my ESP will interrupt my accelerometer, so it's the other way around. Just to initialize my IMU. So you can see I created functions and procedures in this CPP file, but I can use it in my main. So in my main, you'll see here at the bottom, in my setup, I initialize my MMU. And this is not on this page, but on this page. This one. So there we go. So I can make many files actually in Arduino and just call functions. So I've got my MPU 650. So whenever I write a new program that's maybe not the drone, I can just take this file and reuse it. So like we did with the schematics, we spoke about PCBs, making function blocks, you can do the same with code. And then we'll initialize it, it will test it if it can connect to it, and then it will initialize, and then it will do a calibration just to make sure where the 0 is. That's all automatically done. So here you can see that you get a function to get your pitch and roll, and they already got procedures and function for us to do it. But so what we focus on is, if we want rotation, we just use get rotation. They did everything for us. If you want YPR, your pitch and roll, we just use get YPR. So you'll see in my main program, all I did was I want that, and it gets it for me. Amazing how people will do this. Helps us a lot. If you guys want to learn to do it by yourself, then you can use the I2C protocol and actually read the information from the MPU 650 and then do all the stuff yourself. Reading different registers, you can get all this information. So it depends what you want. Do you want to learn to do I2C, or do you just want the drone and learn how to put all the code together to get a final thing working? So different ways of doing it. We live in an amazing world where a lot of stuff is available. But it's always good to understand how it works in case you want to change some stuff. So these numbers are also very important because 34, 22, 21, if you look at my schematic, you will actually see it's over there. It's the same as this, 21, 22, and 34. So this IO21, IO22. So your PCB and your code are quietly, closely coupled, especially pin values. So keep that in mind, guys. Now let's upload the code for the accelerometer and just see what type of values it gives us. As we move the drone, things will change. Let's have a look at that, and I'll explain more about that now. So I just want to test the rotation, the pitch and roll of the accelerometer. So I just have the code output with me, so you can see roll and pitch. It's close to 0, so it's close to flat. So if I move it up a bit, let's say there, then you can see the roll is increasing. And then if I go the other way, the pitch should start increasing. So there you can see it starts measuring the angles like that. So that is basically what's going to happen, and we're going to use those inputs to play around with the PIDs. So let's have a look at our PWM. So like I mentioned earlier, the PWM of the ESP32 is not the same as the Arduino. So the Arduino, to create a PWM, you can just write analog write, and it will output a PWM signal on a certain pin. But with the ESP32, you actually have to set it up in a different way. So to set it up, you need to choose the frequency of the PWM, the resolution. So resolution is like ADC, so you get from 0-bit to 12-bit, but you won't use 0, of course. to 12 or to 16-bit. So the ESP32 can go up to 16-bit resolution for PWM signal. So I just chose 11 and it worked out quite nicely for me. So that just means if I've got an 8-bit, I can go to 256, my value of my PWM. So at 11, I can go to 2096, I think. It's 2 to the power of 11. So whatever resolution you choose, it's 2 to the power of that number will give you the value that you can output. So that is at the bottom here. You'll see I've got, so here I write the speed to my pin, but my speed will not be more than my throttle, and my throttle goes up to 2000. So like I said, 2 to the power 11 is 2096. I'll give you the correct answer when I start editing this video, but it's about there. And then so you can never get more than that. So 2 to the power 16 is like 65,000 something. So that's the importance of resolution. And then here we actually just connect a certain channel to a PW GPIO pin of the ESP32. So they've got, you can, I'll show a picture on the right here where you can see that you have to link a certain pin to PWM, and that's what it does here. Over here you can see I'm setting up my PWM motors, so I can say LD channel 1, 2, 3, 4. So I've got 4 different motors, so I need 4 different PWM signals. And then you can see I can set it up to have a certain frequency and certain resolution, and that's the same with the values that I had on top. And here we go, we attach a GPIO pin to a variable that we have. So this pin is what we set on top, 0 or something, and we attach it to our front left motor, front right motor, right left motor, right motor. So here you set it up, you attach it to a certain value you put in your code. So you guys can see here, and you can see the front left, rear right, front left, rear left is the pins that are used, 12, 14, 16, 18. These are physical pins on the ESP32 that are used for the PW signal. So that's our outputs. So we also made that outputs. As we can see here, we changed pin mode to output. And then you're going to do some PWM signals, and your PWM signals will take your pitch and your roll and change the values of your motors PWM signals to make it balance itself. So that is our actual speed calculations. I'll get into the PWM later, but so basically I'm going to write to just channel my speed, as easy as that. So this is my first motor, as we could see here. So we can see this front left, so it's 12. So when I do that, so 12 is going to be a certain speed, and this speed is then calculated by, the speed is calculated then by our PWM. So you can see I calculate PWM, and then I do some stuff, and my actual speed will be after I stabilize it. I'll get into more details about this. Don't worry too much about it now. Let's just focus on PWM. So that is PWM. You have to set it up. You have to set up the frequency. You have to set up the resolution, and then you have to attach it to a channel to the GPIO to be controlled. And then you attach it, and then you can use it. And you use it by using LCW write. LED C write. So that is the same as analog write for the Arduino. So now you guys know the ESP32 is not exactly the same as Arduino when it comes to PWM signals. So let's look at the Blink application that we use. So the Blink app. So the Blink app is a freely available software that you can download off the Google Play Store or the Apple Store. And it allows you to write easy Bluetooth or Wi-Fi apps for your phone to control Arduino-based projects that uses the Arduino IDE. In our case, we use the ESP32, but we use the Arduino IDE, as you can see. So to make use of the Blink app, you first need to add the Blink app library. So there are many different ones. I just found the Blink Simple ESP32 works quite nicely for me. I'll put the link below where you can download this from, where you can just import the library into the Arduino, where you do add zip folder, you just add the library and then you can include it and you'll have it. So you just have to define your serial name there. So the serial is like, if you go serial.println, most of you guys know about that. So we just give this blink print the property of a serial. And then you have to get an authentication. Then you have to get an auth token. So this will be at the Blink app. Once you register on the Blink app, I'll walk you guys through that as well in this video. But once you register, they'll email you a link and a token, and you put that token in here. And then the SSID and pass is your name of your Wi-Fi network and the password of your Wi-Fi network. So if like our Wi-Fi network name is Plumpot, and then we have a password. I'm not going to say the password, but then we have a password. So that's how. So here it will connect to your Wi-Fi. The app will also connect to your Wi-Fi, and then you can control the drone. And you can just see a function we created to read the joystick. So like I said, the joystick will come from the app, and my throttle, my yaw, my pitch, my roll, and just a button to make start, let's go, we are ready to go. And you can see I use a map function. So what the map function does, it takes my throttle input, which is from the app. I'll show you guys over here, we do it. So then my input that I'm getting from my app is from 0 to 1023. That's what the input gives from the app. But I want this to be represented at 0 to 2000. So the map function actually takes this and changes it to, if I give 1023, it will output 2000. So it changes so what it does, it actually just makes it easier conversion for you. You don't have to write transfer functions, just functions to try to convert this ratio of numbers to this ratio of numbers. It does it for you. So the same with the ref, yaw, pitch, roll. So my input is 0 to 1023. I'll show you guys on the app. But then I want it to be converted to a number between -10 and 10. So 50, let's go. The half of 1023 will give us 0 output. So it's -10 degrees to 10 degrees. That's what we want to be able to control. But as we know, raw data is not in degrees, it's in raw values, and we convert it to degrees in this way. And then my controls active is just a on-off button. So the values from the app, we have to write to variables in our Arduino code. This we use a function called blink write. So you can see VO, V1, V2, V3. Those are virtual numbers on the Blink app that you can set up. I'll show you guys how to do that. So my yaw, I said, is parameter as integer, and please read V0 from my app. Yeah, so this should be V0. Always try to comment, guys. So the same here. So I set in the app, V1 is my throttle and parameter as integer, and I will retrieve. So this keeps reading all that information coming from your app. Then you have to set it up. So if you go to setup, you can see we've got blink.begin, authentication, SSID, and your password. So this is the token you get from the email. This is the name of your Wi-Fi, and this is the password of your Wi-Fi. So now we've set it up. All we have to do now is say blink.run. So when you run it, it will automatically connect to your Wi-Fi, and then you'll be connected on your phone. It's as easy as that. So this runs automatically, and in these functions, it will just keep reading the values that you're getting from your app. So it's very important. So yaw will be a certain value. So that's how you do the Blink app. I'll show you guys now how the Blink app looks, and how the values, how I set it up, how to get that token, and just what I mean by 1024, the functionality, how to set it up, the virtual numbers, things like that. So let's get started with that now. So as you can see on our homepage, we have the Blink app here. So this is the Blink app. You can just go to Google Play and download it over there. So now we'll click on it, click, and you can see what I have currently. So I'll turn it like this. So this is basically how the joystick will be. This is my throttle, up, down, and then my pitch and roll, and my yaw. So this is the button I spoke about. When I push it, it will activate so I can use this joysticks. On the top left here, you'll see that we've got our stop. So when you connect it to it and your drone is on, you can just push play. Here you'll see this one will go away, and because then it's connected to the ESP32 and you can use it. So you have to be in this position to be able to change some settings. So to go to the setting menu, I can just click on any joystick or button I want to change. And here you guys can see what we did in Arduino code, where we spoke about the virtual numbers. So V0, V1, where we had blink right and things like that. And this is the number I spoke about, 1023. So this is the input that my Arduino's or my ESP32 is going to get. And then I'm going to map the values to values that I can use. So for the throttle, we map it to 2000 because our PWM resolution is 11. So we can go up to over 2000. So we cap it at 2000. With the roll and the pitch, we also want to do 3, but we want -10 to 10 degrees. So we map it to -10 to 10. And then you can see how fast it must write. So it must write every 100 milliseconds. That is the fastest currently. And then you can have auto return on or off, or rotate on tilt. So auto return is just, you can see when I push play and I push it like this, it goes back to the 0. This one does not. So this auto returns off and this is on. The reason this is off is because we're going to start the throttle at the bottom and then slowly lift it up to take off. So we don't want it to be in the middle because then it's going to be half the speed of the motors. And then rotate on tilt is when you rotate it like this, your X and Y will just change like a normal phone. So you can also add stuff. With the free version of Blink, you get energy balances and you have to pay to add extra. But for the energy we have is enough for a drone. And here you can see all the different things we can add. Really, really nicely done. So yes, the free version has limited energy, but for us, our purposes, it's good enough. So this will also be available to you guys. I will share the app. You can share it. I will share it. And yes, here you can see it's connected. So you can choose Bluetooth or Wi-Fi. So I will do it over Wi-Fi. And that is our Blink app. Now we're going to talk about the fun part, the PID loop. So this is currently the setup we're currently using. We've got our flight controller, battery, USB 2 program, my phone for the app. And then as you can see here, so it's connected now with the Blink app. So it's stuck now because it won't carry on until I control it with the app. So let's have a quick look at the PID loop. So like I mentioned earlier, the PID just stabilizes the drone. So it tries to get to a set point as quick and as smooth as possible. So by changing these 3 values, I can set the sensitivity and how it stabilizes. I will put video links below that explains it in more details for the ones who want to learn more about PID. So, like I mentioned, these are the values we change. Your proportional, your integral, and your differential. So basically the proportional KP value is just how quickly you want it to get to that set point. So if our set point goes to -10 degrees on the roll, how quickly do we want to get to -10? And if we go too fast, it will overshoot and it will go past the point of no return. KI takes account in your error and it looks into the future kind of. So when it gets to that set point, it will slowly slow down so you can get to that set point smoother and won't overshoot. So KP and KI are quite important. KD kind of looks at the past as well. So it looks at your previous error and your future error. And then also this helps with smoothing out that set point. So these are the values you have to play with. So here you can see, so I'll calculate my roll PID for my proportional by just taking the KP that we add on top times the roll error. And the roll error is just my roll input from the app minus the roll that I actually measure on the accelerometer. So that is my roll error. So like I mentioned there, so KP is just how fast it'll get to the set point. And then KD is taking the error plus your previous error. So it looks back in the past to see how fast it must get to it. So it just helps a lot with not overshooting at the top. So like I mentioned before,
PID for integral just happens close to the set point because it slows it down until you get to your set point. So I only want it active at -3 to 3 degrees. You don't need it earlier because your proportional will just push it there, and as soon as you get close to your set point, the integral will slow it down and then will stabilize at a certain point. So these are the three you have to play with. And there you can see for our motors, we just add the PIDs that we calculated, and then my PWM will change depending on my PIDs. So that's basically the PID. I don't want to go too much detail for it. Like I said, I'll put videos below if you want to learn more. But basically, you just have to change these values to get a perfect stabilized drone.
So here you can see the app. All you do is push play. And now you can see it's connected, because if it's not connected, this will become red. So I just move around, and then when I click this, putting the motors on, and there's my speed of my motor, and you can see it's quite even. So when I make this a bit higher, push it up, you see it increases and decreases. So that's exactly what you want. And you can see it's pretty even all through it. So when I move this a bit to the, so if I move it to there, you can see the one side goes a bit higher, and will keep increasing. So RF and RB is increasing. So you can see here that actually it's trying to make the motors on the right hand side increase so that it can center itself, right? So as you can see, right is getting more and left is getting less. So that is what we want. So basically when I rotate like this, the left hand motors will increase. When I rotate like this, the right hand motors will increase because it needs to push harder to get up here. So that is making sense. But what we want, we don't just want the feedback from the motor, we also want to give feedback from the phone. So if I switch it back on again, as you can see, it's running quite nicely, it's not nothing. And then I increase it, and it's nice and high. Even 1024, 1024, so it's quite nice. So if I move this to the right, let's see what happens. You can see the right hand side is starting to increase a bit there, trying to fix itself. And if I move to the left, and then there we go, the left hand side is busy increasing. So this will tell us to move a bit left or right to 10 degrees. Now we can just make it a bit low again, 0. So I'm still seeing about negative numbers, so I do use the absolute number because I can't send a negative number to a PWM signal. But now what we have to do is now we have to play with the PID values with the drone. So I've got it here, and then I have to see when it starts stabilizing. So that's the next steps. So that is the breakdown of the code. So I spoke about the accelerometer, I spoke about the PWM, a bit about PID. So building this, there's a couple of stuff that I made mistakes with. So the first thing is the batteries. You can't just use any LiPo battery. You need a special, not a special one, but it's made for drones. So these hobby ones will not work. So the batteries has a discharge, a C value, and this discharge is not high enough for the drone. The motors can take a lot of amps. I think it's taking about over 1 amp each, so 4 amps in total, where you can see a drone battery will have 15C at the bottom. Can't see, but that's your discharge rate. So the C is, if you take 15 times by 300 milliamps, you get the amount of current that this battery can supply at any go. And this one can only do 800 milliamps. So when I had this connected, my motor just drained that battery because it cannot give enough, and then it just can't supply power and just fails. So be very careful which batteries you choose. Also be careful with your decoupling capacitors and your voltage regulators. So that motor, well, these 4 motors actually take a lot of current, like I said. So it takes a lot of the current from the battery. So your decoupling capacitors, you need to add a nice strong one just to make sure that your line is stable. So that's why you can see I actually modded an extra 470 microfarad capacitor. So we spoke about decoupling capacitors before. It just keeps the charge like a little battery. So when there's a little dip, it will keep that battery power there. Also make sure your voltage regulator, volt drop is LDO. So it's low drop dropout voltage. So if I've got a 3.7 volts input and I've got a 500 millivolts drop, then my output is 3.2. That's very important because the voltage regulator I used, it's set it at 50 millivolt drop, but that's not a full current. So at full current, so when I run this at full current, I've got a 0.5 volt drop. So if my battery goes to 3.7, I get about 3.2 out. So if it goes below that, the ESP32 goes into a brown out. So that means it shuts down under 2.8 volts. So that can easily happen. So, and these batteries, these drone batteries, drain very, very quickly. So what I do now is I fully charge it to 4.2. Then I got a volt drop of 3.7, which is fine. And I just run it for a short while, because when I run it too long and it hits brownout, my motors stay on and this thing goes to the roof. Just so you guys know. So I made mistakes. I am busy with version 2. You guys can join me on the weekends live stream. I'm busy updating it, choosing a new voltage regulator. So this does work, this PCB. But yeah, just be careful with running the battery too high and with a volt drop. That's one issue I found with this PCB. I'm honest with you guys. When you make a PCB design, there's always some first time right. I don't know if that ever exists. But other than that, it worked quite well. So the accelerometer is fine. Voltage regulator. I'm going to add a battery charging to the circuit as well. And then I'm going to make a form fit function. So it just clicks on these. So you can buy this housing and just click it on. So that's my idea. We're also going to try a 3D print one and then try to fly that. Great guys, thanks so much for watching. If you lasted this long, well done, because I can jumble and talk about all the different stuff and go off topic this way and this way. So you made it, you're quite interested in this stuff, so thanks a lot, appreciate it. So yeah, see you guys in the next video. Please guys, always send me messages if you have any questions about PC design, about electronics. I reply to everyone on Instagram. I should not say that, but I do. Join our Discord, nice to chat to you guys, and then see you guys on live stream. Ask me any questions. I'm going to make version 2. So the next project after the drone is my macro keyboard. So that arrived. So yes, the macro keyboard arrived. I don't know if you guys remember, we did this on live stream. So it's basically a little Streamlab stream deck, just with a nice screen. So you guys can see that also live stream. I'm going to make a tutorial about this as well. Same with the drone. PCB programming, break it down, give you guys the files. So whatever we design on PlumpPod, I'm giving to you guys. Okay, I'm talking too much now. Guys, have a fantastic day, fantastic night. Until next time, bye.